Hello, welcome to this presentation. This is an introduction to the x86 architecture, as well as a comparison between VAX, Alpha, Itanium, and x86 from an OpenVMS point of view. This presentation was previously delivered at the OpenVMS Bootcamp 2016 in Nashua, New Hampshire. Here's a small disclaimer that I need to include in all of my slideshows, so don't worry about that. So to begin with, just a little bit about myself. I'm a software engineer at VMS Software. I guess it's safe to say that I'm a bit of an expert in x86 architecture as well as the C and C++ programming languages. And my work at VSI is mainly on the x86 port, and in particular the Swiss bits of it. And I'm also involved in the Java 8 port. Before I joined VSI, I was the architect and developer of a number of alpha emulators, and I also have some experience as a contractor using OpenVMS in various industries. Besides work, I like to collect old hardware, and I'm particularly fond of big old hardware. I like playing with electronics and FPGAs, and I have a bit of a wine collection, so it's very useful that my wife and I bought a 200-year-old farmhouse 3 years ago with a lot of barn space and a wine cellar. So in this session we're going to be talking about computer architecture, and the word architecture as related to computer systems was coined by the architects of the IBM System 360 range of computers, and they describe architecture as the attributes of a system as seen by the programmer, which means the conceptual structure and the functional behavior of the system. Computer architecture does not relate to the organization of the data flow, the controls, the logical design, and the physical implementation. And this word was particularly useful for the IBM System 360 because the System 360 was a 32-bit architecture, but they designed from the beginning a whole range of different systems, and some of them had 8-bit internal components, others were 16-bit internally, others were 32-bit, and the largest systems were 64-bit internally, yet they all exposed the same 32-bit architecture to the programmer, and that's the level of abstraction that we're interested in currently. So let's have a little look at where x86 came from. After that, we'll have a quick comparison between the different architectures, and then we'll go into more detail after that. So let's start off with just a little joke I put together for this presentation. And as you can see, they are everywhere, and they are pretty much everywhere in real life. They're in my laptop, they're in my desktop systems, you find them in large servers and even in large multi-CPU supercomputer systems these days. So if we want to take a look at where the x86 64-bit architecture came from, we need to go all the way back to its humble beginnings in 1978, when Intel released the 8086 processor, which was the processor that ended up being the heart of the IBM PC. Shortly after the 8086, Intel released the 8088, which was identical to the 8086 except for the part that it had a 8-bit external data path rather than a 16-bit one. In 1982, the 286 processor added something known as protected mode, which provides memory protection features and paging. 1985, the 386 took this to be a 32-bit architecture, very big step. The 486 and the Pentiums are basically further developments of the 386. The underlying microarchitecture changed and there were small additions to the instruction set, but the overall architecture didn't change much from 386 to 486 and Pentium. Then in 2001, Intel released the first Itanium processor, Merced. And Intel's idea was that everyone would flock to this processor. However, it wasn't as successful as Intel had hoped, and in 2003, AMD saw an opportunity to release a 64-bit processor that was fully backwards compatible with the 32-bit 386. So they added a 64-bit mode to the 386 architecture and released that as the Athlon 64 processor in 2003. So this was the beginning of the AMD 64 architecture, and this is the first case where Intel was more or less forced to adopt an architecture extension that was developed by AMD. Before then, AMD had been copying Intel as far as architecture goes, and this time it was the other way around. So if we want to compare the x86 to the VAX Alpha and Itanium processors and architectures, the first thing that comes to mind is that the VAX, the Alpha, and the Itanium can all stand on their own 2 feet. They're all clean, new designs. Of course, the 32-bit VAX had some compatibility with the 16-bit PDP-11, but nonetheless it was clearly a new architecture. However, if you look at the AMD 64-bit architecture, they started with a 16-bit architecture, added the 286's protected mode to that, then added 32-bit 386 architecture on top of that, and finally they added 64-bit capabilities on top of that. So this is really an extension to an extension to an extension of the original 16-bit architecture. So this leads to some strangeness in this architecture, which we'll explore later on. Architectures. The 3 main architectures are the 16-bit x86, the 32-bit IA32, and the 64-bit x86-64. And there are various sub-architectures of each of these architectures, starting, of course, with the architectural changes that were made in the 286, which added protected mode to the x86 16-bit architecture. And various other architectural changes were added in processors like the 486 and the 586 and the 686. So these are the names of the sub-architectures, and then the third column gives us the name of the first processor that has these changes in them. And as you can see in the case of Intel, they started out with numeric names up to 8486, and then after that they started having fancy trade names like Pentium and Pentium Pro. The final column gives some other implementations that implement the same architecture. So the 8086 again is the same as the 8086 but with an 8-bit data path. The V20 and the V30 were basically clones made by NEC. AM386 and AM486 were AMD clones of the Intel 386 and 486 chips. And then there are various other names that you can see in those lists. So there is a little bit of confusion as to what we should call this architecture. When AMD developed it internally, initially they called it x86-64. By the time they released this to market, their marketing department had changed that name to AMD 64. When Intel adopted AMD's architecture, they called it EM64T. Later on, they added the term IA32E, with the E for extended, to their documentation to refer to the 64-bit long addressing mode that the EM64T processor architecture was capable of. And more recently, they dropped the name EM64T in favor of the new name Intel 64. Another name that you saw occasionally, more or less as a joke, was iAMD 64, which was of course the AMD 64 trademark with a small I attached to it, the way Intel liked to put together their trademarks. And then finally some others, Microsoft Sun and UEFI firmware, refer to this architecture as x64, which is nice, short and sweet. So the one thing to remember of all this is wherever you see one of these names, they essentially mean the same thing. Now, there are a lot more names that we see for more modern processors. And we need to distinguish between brand names and microarchitecture names. So both Intel and AMD have brand names for their processors. These are names like Xeon, Core, Pentium, Atom, Opteron, Athlon. And these indicate what the intended use of the processor is. So for instance, Xeon and Opteron are used to refer to server chips. So these typically have higher memory bandwidth, more RISC features, possibly. Names like Core and Athlon, on the other hand, refer to desktop processors. And names like Celeron and Sempron refer to laptop processors, so these tend to emphasize low power more than the server chips. Now, these brand names don't say much about the internal organization of the actual processor core. This is where the microarchitectures come into play. So Intel is following this Tick-Tock model where they come up with a new microarchitecture. Core is one, for instance. And then after coming up with a new microarchitecture, the next step is to shrink that microarchitecture so it can run at a higher clock speed. So Penryn is essentially the same microarchitecture as Core, except that it's been shrunk so it runs at a higher clock speed. Then the next step after that is a new microarchitecture, Nehalem in this case, which then gets shrinked again, and it becomes Westmere. So this is Intel's Tick-Tock model. What is important to note is that the transition from 16-bit to 32-bit and now to 64-bit was not the only change to the instruction set that was made over the years. In this slide, I've got a few of the instruction set extensions that were added to the x86 architecture over the years. These are not all the extensions that were made, but these are ones that are particularly interesting, so I'd like to go over them with you. So the x87 coprocessor was added in 1980. This was a separate chip that you would plug into your mainboard next to the 8086 processor, and this extended the 8086's instruction set with floating point instructions and provided floating point registers and operations. The 8286 added protected mode in 1982. This was the first use of virtual memory on the 8086 architecture. And of course, the 8386 added 32-bit processing in 1985. In 1995, the Pentium Pro added physical address extension, which made it possible to address more than 4 gigabytes of physical memory from the CPU. And in 1997, Intel added MMX to the Pentium MMX model. This is a set of instruction that uses the floating point registers to do single instruction, multiple data instructions for integer operations. So these are used for multimedia. In 1998, AMD added a different way of doing single instruction multiple data in the form of 3D Now, which was a floating point implementation. This didn't see much adoption, at least not in the mainstream, because Intel didn't follow suit. And this is the only one of these extensions that are no longer available in current chips. In 1999, with the introduction of the Pentium 3, Intel added SSE, or Streaming SIMD extensions, which is also floating point, single instruction, multiple data, introducing a whole new set of registers specifically for this purpose. SSE also adds the capability to perform integer instructions on the floating point registers. And it also allows you to do some scalar floating point operations on the XMM registers. The Optron, of course, was the chip that introduced 64-bit addresses in 2003 and 64-bit registers. And then in 2005 and 2006, both Intel and AMD came out with virtualization support in the form of VTX and AMD-V. Now, if you are writing a hypervisor, it's worth to note that even though the principles that these two instruction set extensions provide are similar, the implementation is different and you need to use different code regarding, depending on whether you're running on a system with VTX or with AMD-V. 2010 in Westmere, Intel added the support for the advanced encryption standard. This added some instructions to take care of common cryptography operations to make those go faster. And in 2011 in Sandy Bridge, Intel added the advanced vector extensions, which made the XMM registers larger and added extra extensions to the SSE instruction set, basically. In 2003, Intel added TSX, transactional synchronization extensions. This is a mechanism to avoid a lot of locking of memory structures. And even though this was introduced in Haswell in 2013, Intel soon discovered that there was a bug on the chip and they couldn't fix it in a microcode update. So instead they opted to deliver a microcode update that effectively disables this feature in Haswell and Broadwell processors. And it's recently been reintroduced in Skylake processor where TSX does seem to work. Skylake also added the MPX, memory protection extensions, which is a way to do bounded memory access, which should help prevent buffer overflows and buffer overflow exploitations. Now that we have reviewed the history of the x86 architecture, it's time to start comparing it to VAX, Alpha, and Itanium. But before we do so, I should point out that even though the x86 has 16 and 32-bit modes, these are not the modes you're looking for. We're only interested in the 64-bit operating mode of the x86 architecture. So some numbers. Word size, we're familiar with 64 bits and that remains the same on x86. The architecture. The VAX was a complex instruction set architecture and with a lot of different instructions, about 460, a lot of addressing modes, about 24, variable length instructions, and so the Alpha was a typical RISC processor with far fewer instructions, about 135, a very limited set of addressing modes, about 4 if you count them liberally, and a fixed instruction size of 32 bits. The Itanium 2 was a little bit odd. This was an explicitly parallel instruction set computer, which basically means that the compiler needs to tell the processor what it can and cannot do to optimize the code. About as many instructions as the Alpha, 6 addressing modes, and fixed bundles of 128 bits that contain 3 instructions or syllables each. The x86, we're basically back to the VAX days. This is a complex instruction set computer again, although as we shall see shortly, it has an underlying RISC-like core that executes micro ops, which makes this sort of a hybrid. The x86 has a lot of instructions, even more than the VAX. Depending on how you count it, it's over 600 instructions. The x86 has 10 different addressing modes, and the instruction size is again variable. The number of registers. So the VAX has 16 general purpose registers that are used for both integer and floating point. The Alpha takes this up to 32 registers plus 32 dedicated floating point registers. The Itanium 2 has 128 of each. And then when you get to x86, we've got 16 general purpose registers, 8 MMX registers, and 16 XMM registers. So we have 16 general purpose registers. We do not have the instruction set orthogonality that we had on VAX and Alpha, which means that you can basically use any register in any context. So on the x86, some of these 16 registers have specific meanings, which means you cannot use them for just anything. And then the MMX and XMM registers can be used for floating point, and in some cases they can also be used to hold integer values. Finally, even though that's not really part of computer architecture, it's interesting to note how the number of transistors on a chip has grown. The VAX processor with the largest number of chips was the NVAX, which had 1.3 million transistors. Alpha, in its EV7 incarnation, has 130 million transistors. The Paulson chip has 3.1 billion transistors, and finally the E7 V3 chip on x86 has 5.6 billion transistors, although these make up more cores, of course. So I want to go into the difference between CISC, RISC, EPIC, and modern CISC or x86 CISC in a little bit more detail. So if you look at a traditional CISC architecture like the VAX, we have complex instructions that mix computation and memory access. So in one instruction you can fetch two operands from memory, add them, and then write them back to memory, and the addresses in memory that you reference may actually be the result of a fairly complex computation themselves, and all this can be done in just one instruction. So because of this complexity, most of these chips, apart from the very simple ones, tend to be microcoded, which basically means that the processor itself runs through a program that fetches instructions, decodes them, and then executes them. This step-by-step microcoded implementation makes optimizing code execution by the processor itself difficult. So typically one of these CISC processors will not do a lot of things like reordering instructions or execute multiple instructions in parallel. When you get to a RISC architecture, which is a reduced instruction set computer, you now have very simple instructions. So if you want to fetch some operands from memory, add them, and then write them back to memory, you now first need to have some instructions to calculate the memory addresses. Then you'd have two instructions to fetch the two operands from memory into a register. Then you do the computation on those registers, and then you write one of the registers back to memory. So you need several instructions to accomplish the same thing. However, because these individual instructions are so simple, it now becomes feasible to hardwire the control logic for these instructions. And also because they're fairly simple and these instructions have no or very few side effects, it becomes relatively easy for the processor to do a lot of optimization, like parallel execution, pipelining, reordering of executions, and branch prediction. However, as we progressed through the years, the optimization hardware to do this was becoming increasingly complex. And if you look at like an EV7 chip, and you look at what the silicon real estate is used for, you will find that only a small portion of the chip is actually doing the computations, and a large portion of the chip is there to do all of these optimizations. So this was making RISC processor development expensive. And the idea that Intel had when it came with the Itanium, or the explicitly parallel instruction set computer, was that we could shift some of this burden to the compiler writers. So again, we have fairly simple instructions. We separate computation and memory access. But rather than the processor going off on its own and determine this is stuff I can safely execute in parallel, the parallel execution is done based on compiler inserted stops. So the compiler will put a stop bit between certain instructions, and that's a signal to the processor that basically the processor can assume that anything that does not have a compiler inserted stop bit between them can be executed in parallel. Another novelty in the Itanium is the use of predication. This means that you have some predicate bits that you can set based on, say, a comparison. And you can tag instructions with one of these predicate bits, which means they only get executed when the predicate evaluates to true or false. And that means that you can do a lot of conditional execution without actually branching. And branching is something that's expensive because branching typically involves flushing some of the pipelines in the processor and maybe throwing some of your instruction cache away. Itanium chips initially were mostly hardwired, although there is a fair bit of microcode involved as well. And the burden of optimizing was shifted to the compiler. Although the latest generation of Itanium chips, the Polson, fixes some of that by doing some reordering itself. So now we get to the modern CISC architectures like the x86. And here we still have the same complex instructions we had on the VAX, except they now get translated into RISC-like micro-ops. And these are very small, simple instructions. So one x86 instruction may translate into something like 5 or 6 different micro-ops. This can be partly hardwired, and because we now have these simple instructions again, we can do the same kind of optimizations we could do in RISC chips. And Intel really has been pushing the boundary of what they can do in terms of optimization. So they do parallel execution, reordering, pipelining, and branch prediction after they've translated the Intel instruction into these micro-ops. And they're just dedicating a whole lot of chip real estate to doing these optimizations, and they were able to do things that we couldn't dream of 10 or 20 years ago. The register set. I'll go over this fairly quickly. The VAX Register Set, 16 general purpose registers, although in VMS, of course, some of these do have special purposes like the program counter and the stack pointer. A processor status long word and several internal processor registers are to support the operating system. The alpha, again, 32 general purpose integer registers. Some of those have a dedicated meaning within the context of OpenVMS. 32 floating point registers, a dedicated program counter, a processor status word, and internal processor registers again. So on Itanium we have 128 general purpose integer registers. We've also got 128 floating point registers, 128 predicate bits, 8 branch registers, an instruction pointer, the user mask, and then again several internal processor registers for the operating system's use. So now that we get to x86, we have to scale our register use back a bit because now we have fewer registers to play with, and in fact it's looking pretty much like we're back on a VAX, certainly on the integer side. We now have 16 general bit integer registers, and some of these have a special purpose, like the RSP, which is used as the stack pointer. And if you're moving data around in memory, you're probably going to use instructions that require the source index to be an RSI and the destination index to be an RDI. In addition to those integer registers, we have two different sets of additional registers. The first set is the MMX and original floating point registers. These are used by MMX instructions, which are single instruction multiple data integer instructions, as well as by the original x87 floating point instructions. Later, with the addition of the SSE instruction set, we got 16 XMM registers, which can originally were up to 128 bits in size, but currently can be up to 512 bits in size. And these can be used for single instruction multiple data floating point values, but the instruction set also allows these registers to be used for simple floating point operations, using a nicer mechanism than the original floating point available in x87. The SSE extensions also allow the MMX registers to be used in some simple integer operations. Then we have the instruction pointer, RIP, the flags register, and again a whole bunch of internal processor registers that the operating system uses to interface with the CPU. An oddity of the x86 instruction set is the ability to address various parts of a register. And this, of course, is a result of the fact that they started as a 16-bit architecture. So the original 16-bit registers had names like AX. And of the AX register, you could address the high 8 bits as AH and the low 8 bits as AL. And then when they went to a 32-bit architecture, the AX register got extended and became the extended AX register, or EAX. And then when they went to 64-bit, it became known as RAX. But you can still address the 32-bit EAX subpart of it, as well as the 16-bit AX subpart and the 8-bit AH and AL subparts of it. With the newer registers, R8 to R15, this still is pretty much the same, except that you cannot address the one but lowest 8 bits. So there's no equivalent of the AH part of those registers. So instruction encoding. This is where things start getting really funky. So VAX instruction encoding is simple. You have 1 or 2 bytes of opcode, and one opcode uniquely identifies an operation. After the opcode, you get the operands. There can be a number of operands, but each operand looks exactly the same. So there's 1 byte which contains the addressing mode and a register number. And that, depending on the addressing mode, gets followed by up to 4 bytes of displacement, immediate data, or address. And of course, there are addressing modes in which there is none of that. So in that case, the operand is just 1 byte long. Alpha, of course, instructions are always 32 bits long. The first 6 bits of those are an opcode. And the operands are encoded in the remaining 26 bits. So here we can encode up to 32 registers. There can be a 20-bit displacement in there. It can contain an 8-bit literal value. And there can also be a function specifier in it, because in some cases the 6-bit opcode only identifies the class of the operation and not the operation itself, and in that case additional bits are required to encode the actual operation to be performed. In Itanium, we have a 128-bit bundle. The bundle contains 5 bits that are a template, which basically tells the processor which of the syllables in the instruction can be handled by which type of execution unit in the processor. And then we have 3 41-bit syllables or instructions. So these consist of 4 bits of opcode, 31 bits for the operands, and in most cases the operands are a 10-bit function specifier, because in this case again the opcode doesn't uniquely specify the operation to be performed, as well as the encoding of 3 registers. And finally there are 6 predicate bits, and these select the predicate that determines whether or not this instruction gets executed. So on x86, this is where the instruction encoding gets very interesting. So to start with the opcode, opcodes can be 1 to 3 bytes long. And originally opcodes were 1 byte long, and when Intel started filling up their opcode map, they figured out they'd run out of space, so they said, well, if the opcode starts with this hex value, then it's a 2 byte opcode, and later if those 2 bytes were a certain value, then it would actually indicate a 3 byte opcode. The opcode gets followed by a mod RM byte. That's 1 byte that specifies the addressing mode, and it can either specify 2 registers or a register and a 3-bit extension to the opcode. If the mod RM byte specified indexed addressing, it gets followed by a SIB byte, which is a byte that specifies the scale factor and the index and base registers for indexed addressing. So using that SIB byte, you can have something like take this constant value plus 8 times the contents of this register plus 1 time the contents of this register, and use that as the effective address. And then finally there can be 1 to 8 bytes of displacement or offset, and 1 to 8 bytes of immediate value in an instruction. Now, there can also be something in front of the opcode, which are prefixes. So those can be up to 6 bytes long, and these specify things like the address and operand size. So for instance, if you want to use 64-bit registers in your instructions, you have to indicate that using one of these prefixes. If that prefix is not there, the instruction gets treated as a 32-bit instruction. Also, if you want to use any of R8 to R15, you need to specify that with a prefix. There are some instruction set extensions that are indicated by the use of a prefix. And finally, prefixes get used to indicate locking, repetition. It can be used for branch hints, and it can also be used to reference memory in another segment than the data segment. So fairly complicated instruction encoding here. And there's an architectural limit of 15 bytes on the length of an instruction. So even though you could theoretically come up with an instruction that doesn't fit in 15 bytes, if you were to issue an instruction like that, the processor would, at the beginning of its processing, recognize that this instruction is over 15 bytes, and that would result in an exception. So the memory layout and memory management on these different processors. So like Alpha, Itanium, x86 has a 64-bit address size. And also like Alpha and Itanium, but unlike the VAX, it has a split virtual address space, which means that not all of the bits in the address size So not all of those 64 bits are actually implemented. On Alpha, 48 of those bits were implemented, on Itanium 54 bits, and on x86 48 bits. So that means that you have addresses that are not valid. And so you have if you take the entire 64-bit virtual address space, there's a number of addresses at the bottom that are valid. There are a number of addresses at the top that are valid, and everything in between that is an invalid or a non-canonical address. So a valid address starts either with 000 or with FFF. Page sizes are different. On VAX, pages are always 512 bytes. On Alpha, you have a number of different choices using granularity hints. On Itanium, the size of the page can be anywhere between 4 kilobytes and 4 gigabytes, all left to the discretion of the operating system designer. And on x86, we have 3 discrete possibilities: 4 kilobytes, 2 megabytes, and 1 gigabyte. VAX uses 2 levels of page table, Alpha and Itanium use 3 levels, and x86 uses 4 levels of page tables. The physical address size is also different. While the VAX offers a 32-bit physical address size, Alpha 44 bits in EV7, Itanium 50 bits, and x86 currently supports 48 bits of physical address size, although the architecture can go up to 52 bits. On x86 we also have something known as segmentation, which is not entirely there anymore when we run in 64-bit mode, but there are still some remnants of it. And some of that we will have to use within the operating system for some purposes. So that's another level of page protection that we need to, or memory protection that we need to concern ourselves with. And finally, on x86 we have fewer bits in the translation lookable site buffers and in the page table entries to indicate the page protection. So we only have 3 bits, 1 bit to distinguish between a readable and a writable page, 1 bit to distinguish between a user mode accessible and a supervisor mode accessible page, and 1 bit to indicate that this the data page contains data that should not be executed. So what I would like to look at now is how VMS maps onto the hardware and where the boundaries are between hardware, firmware, and the operating system. So if you look at the original VAX, the 11780, it's got a CPU that implements the Q instructions in hardware. The console is also a separate piece of hardware in this case. In the VAX 11780 that was a PDP-11 that was part of the system, and then of course there's a little bit of firmware that runs on top of that console system to actually run a program, but most of what the operating system had to interact with was pure hardware. Now on the micro VAX they economized the hardware console away, and the console now became implemented in firmware running on the actual CPU. So you still have your Q instructions in hardware, even though on some micro VAX models that gets executed as microcode, but it's not part of the firmware that's written in the CPU's instruction code. When we got to Alpha, the whole purpose of Alpha was for it to be a very clean RISC design. So there was no place for things like Q instructions or console implementation in the CPU itself. So on Alpha, the console function is executed by the SRM firmware, and things like the Q instructions and some other parts which were previously part of the operating system are now part of something called PAL code, which is an element of alpha firmware, and PAL code can be regarded as an extra privilege level underneath kernel mode. So if kernel mode is ring 0, then PAL code would run in, say, ring -1. And PAL code has access to the internal processor registers of the actual CPU itself, and in return it exposes to the operating system a set of internal processor registers that look a lot more like the internal processor registers that you had on a VAX. And PAL code also implements things like the Q instructions. So PAL code cannot be interrupted on alpha, and PAL code can use some special instructions that the normal operating system code cannot use. When we went to Itanium, and now when we are going to x86-64, the picture is going to be the same on both those platforms. And the picture there is that the console is now called the UEFI, but there's no more place for PAL code built into the platform to support the operating system. So what we had to do in the port to Itanium is we had to take that PAL code functionality and make it part of the operating system. So as part of the operating system software, we now have implementations of things like the Q instructions, but also code to handle things like software interrupts, ASTs, and to do a lot of the exception and interrupt processing that was done in PAL code on the alpha. And this also includes parts of memory management. So these boundaries are a little bit different, and we're just doing a lot more in the operating system now that used to be part originally of hardware, later part of firmware, and it's now part of the operating system software. RAS features. I took a look about a year ago at the different RAS features that were then available in the Itanium processors, and there are a lot of them, but I sort of grouped them into the most important ones. And then I went searching the Intel literature to find out which of these are available in the Xeon processors. And what I found out is that in the high-end Xeon processor, pretty much all of these RAS features are present. The only one I couldn't find was the internal logic soft error checking, and that appears to be coming in the upcoming Skylake EX processor. What is important to note, however, is that simply the fact that the processor implements some of these RAS features doesn't mean that you can get these features out of just any x86 server that has this processor. You need support in firmware, you may need extra hardware support for this, and to my knowledge, one of the very few platforms that offers most of these RAS features is Hewlett-Packard's Superdome X system. So finally, I want to have a look at the proliferation of x86. Why has this chip survived for so long? So in this slide, I've attempted to show the lifespans of different architectures. The yellow bars are where the architecture was in development. The light green bars are where the architecture is available, still being actively developed, and VMS does not run on it. Dark green is the same thing, but VMS does run on it, and the orange bar is where the architecture is no longer being actively developed, but you can still buy the last generation of chips from the vendor. So if you look at Alpha, for instance, you can see that it only had a pretty short lifespan where it was being actively developed. And if you look at x86, it's been going on for a much longer time. To answer the question why x86 has been so successful, I think we need to follow the money. and this is a look at the 2013 server market. And as you can see, about 3/4 of all server revenue goes to x86 based servers. But if you look at the number of units shipped, the x86 server market makes up over 95% of the entire server market. And if you add to this the millions of consumer devices based on the x86 architecture, you can see that it's really worthwhile for Intel to invest a lot of money into this architecture, simply because so much of it is sold continuously. So if you look at the graph at the right, you can see that the x86 servers are a lot less expensive than RISC and Itanium servers, and they're a whole lot less expensive than the other servers, which are mainly IBM mainframes. But because of the sheer volume that they make up, there is a huge profit to be reaped from selling these servers and selling these chips, which allows Intel to keep making the kind of investments that are needed to keep this architecture going forward, whereas a lot of the other vendors have struggled to gain enough market volume to get enough of a return on investments in those chips to keep them going forward. And I think that's the answer to the question. Thanks for your attention, and I hope to see you at the next bootcamp.